Hello, good day to everyone. Our lecture for today is about the application of the voltage law and then the current law to analyze a given circuit, direct current circuit. As you can see it here on the board is a given circuit wherein we will be analyzing the voltage and then the current using the direct application of the voltage law and then the current law. Basically, class, there are only two ways to analyze a circuit. Number one is by applying the circuit reduction method, but this circuit reduction method applies only to circuit that contain only one voltage source. In the case of circuit that contains two or more voltage sources or current sources, then the method cannot be applied anymore. However, the analysis may be with the direct application, of course, of the voltage law and then the current law. As I've said, we are going to study together this afternoon this direct application of the voltage law and then the current law. I presume that you have already an idea of the circuit reduction method as well as the Ohm's law as well as the voltage law and then the current law. The voltage law simply states that around any closed path of an electrical circuit, the algebraic sum of all the voltages is zero. And then the current law states that at any point or junction of an electric circuit, the algebraic sum of all the current is also equal to zero. Now, as shown here on the board is a simple three-loop circuit, because there are three loops, 1, 2, and then 3. And then let us say that we would like to analyze the values of all the branch current as well as the voltage across each element of the circuit. So let us say our required is all branch currents and then letter B all voltages across each resistor. Solution. Take note that in analyzing a circuit, the first step that you are going to do is to introduce or assume the direction of current in each branch of your circuit. In this case, we may assume any direction. Aside, the direction of the current, of course, is of your choice. You may assume in any direction for as long as you have correctly placed or assume likewise the polarity of the voltages along each element of the circuit. Say for example, let us assign the current. Let us say the current here is I sub 1. The current here is I sub 2. Here is I sub 3. Along this 8 ohm resistor is I sub 4. Here, the current direction is to the left, I sub 5. And then to the last branch, let us say this is I sub 6. Now, as I've said, it is your choice, of course, to direct the branch current and the circuit. The only thing that you have to consider is that all branches of the circuit must be provided with the current. And then after assuming the direction of the current, the polarity of the voltages along the resistors should likewise be considered. Take note that the polarity of the voltage across any resistor in the circuit or any element in the circuit should be consistent to the direction of the current that you have placed along the circuit. Say for example, let us say the 2 ohm resistor, considering the 2 ohm resistor, I sub 1 will be flowing to the right, and therefore the voltage that V sub 2 must be marked plus minus as shown. Meaning, to the left, at the entrance of your current I sub 1, the voltage drop must be provided with a positive sign, and then to the right of 2 ohm resistor, the voltage must be given a negative sign. Take note na considering the voltage across the resistor, the voltage is always determined using the direction of your current. And take note that wherever is the entrance of the current considering the resistor, it is always the positive terminal, meaning the current leaves the resistor at the negative terminal. And then considering a voltage source is of course a source of current. The current of the source must leave the positive terminal, going to the external circuit, to the load, and then back to the negative terminal. And then we proceed as follows. Because the current across the 4 ohm resistor is going down, the voltage across this resistor V sub 4 must be provided likewise with the positive and the negative sign as shown. Considering the 8 ohm resistor, it should be V sub 8 plus minus, consistent likewise to the direction of your current. In the 1 ohm resistor, this is V sub 1 plus minus. In the 10 ohm resistor, it should be V sub 10 plus minus. And V sub 5 to the 5 ohm resistor plus minus. Take note that all the polarity markings indicated here in the circuit diagram are all consistent with the direction or the assumed direction of the current. Now, after indicating all the currents in the circuit as well as the voltage drop across the element, each element, all you have to do now is to apply the voltage law to each closed path of the circuit, and then likewise apply the current law to each of the intersection or nodes of the circuit. But take note that in applying the voltage and then the current law, the purpose why you have to apply it to a closed, the voltage law to a closed path and then the current to intersections or nodes of your circuit is this, because you would like to formulate or form equations sufficient to the required number of unknowns in the circuit. In this case, as you can see it, there are 6 unknown currents in the circuit: I sub 1, I sub 2, I sub 3, I sub 4, I sub 5, and then I sub, by the way, may I correct this one? Yes, I sub, V sub 5, and then I sub 6. 6 unknown currents. You do not have an unknown voltages. The voltages can be determined later, the moment we have already the values for the currents. That's the time that we determine the corresponding voltages across each resistor. But for the meantime, we have 6 unknown currents that you have to determine. And to be able to determine this current, what you need is to form at least 6 independent equations, so as we can make use of this independent equation, 6 independent equations to solve simultaneously to obtain the values of this unknown current. Now, in applying the voltage law, I would like to advise you to apply it only to limited closed path, or if possible, apply it to the closed path using the loop of your circuit. In this case, you have 3 loops, so you can write the equations, the voltage law, along the first loop, the second loop, and then the third loop. Now, to facilitate the writing of your voltage law and then the current law, of course, it is advisable that you put some markings on the nodes of your circuit, so as to guide us on how to trace the voltages along closed path, as well as the current as applied to the nodes. Say, for example, we may label the circuit as shown: A, B, C, this is D, E, and then F. Actually, A and E are at the same potential, so you can just consider it as a single point, although you can just put it there. Now, after this one, we are already writing the voltage law and then the current law. I made mention a while ago that the voltage law should be applied to, as much as possible, to the loop of your circuit. Although you can write as many, I think 6 equations using the voltage law alone, but I would advise you to make use of the loop only. I have reasons for that. I will show it to you later. Now let us say, apply the Kirchhoff voltage law to path, say A, B, C, D, meaning from A to B to C to D to E and then back to A. This is a complete closed path of your circuit. So when we write the voltage law, of course, starting from A, we say going from A down to B, we meet the 48 volt source, and that the 48 volt source is negative at A and then positive at B. So we place positive sign for the 48 volts. And going through from B down to C, you will cross across V sub 2 from positive to negative. So you place negative sign, V sub 2. And then from C down to D, V sub 4 is to be traced from positive to negative. So this is again negative V sub 4. From D down to E, negative V sub 8, because you are tracing the voltage V sub 8 from positive to negative terminal also. And then from E down to A, there is no element. So down to A, you have already completed the entire closed path. So you say 0, because according to the voltage law, around any closed path of an electric circuit, the total voltage, the algebraic sum of the voltages is always equal to 0. Now, this is now 48, And we know that the voltage across the resistor is of course equal to its current multiplied by the resistor. It should be 2 times I sub 1. Ang V sub 4 is 4 I sub 4. V sub 8 is minus 8 I sub 4 I sub 2 and minus 8 I sub 4 is equal to 0. And then dividing both sides by 2, you will have 24 minus I sub 1 minus 2 I sub 2 minus 4 I sub 4 is equal to 0. And if you want to, you may write here, we can say now that this is equation 1. You already have equation 1. Now, the next one is we apply the voltage law to path, say starting from D down to C to F and then to D and then to D. The voltage equation will be starting from D down to C. The voltage V sub 4 is to be traced from negative to positive. So we say positive V sub 4. And then V sub 10 is positive to negative. It must be negative V sub 10. And then the 8-volt source will be traced from negative to positive. It must be positive 8. And then the 1 ohm, the voltage drop to the 1 ohm resistor will be traced from positive to negative. It must be negative V sub 1 again is equal to 0. And then let us apply the voltage law to path. The next path is, shall we say, D to F, to E, and then back to D. The voltage equation, as you can see, it will be written as positive V sub 1. See that? This is from D to this point is negative to positive V sub 1. The 8-volt source will be traced from positive to negative. It becomes negative 8. From here, from F down to E, the V sub 5 will be traced from positive to negative. So it must be negative V sub 5. And then the voltage V sub 8 will be traced from negative to positive. It must be positive V sub 8 is equal to 0. And then by the way, we're not yet through with the voltage equation for the second part. V sub 4, let us supply the values. V sub 4 is 4 I sub, what's this? V sub 4, 4 I sub 2. It should be 4 I sub 2 minus V sub 10 is 10 I sub 3. 10 I I sub 3, and then plus 8 minus V sub 1 is 1 I sub 5. 1 I sub 5. So equals to I am referring to this one, the second application of the voltage law to the second loop. I forgot to supply the values. The values now, as you can see it here, dividing both sides by 2. The equation will be reduced to 2 I sub 2 minus 5 I sub 3 plus 4 I don't know, we cannot divide both sides by 2. Never mind this. So let us consider now this as equation number. Okay, to continue for the last loop, or the third loop, this one, I am referring to this as the we now supply the values for the voltages. V sub 1, of course, is 1 I sub 5 minus 8. V sub 5 is 5 I sub 6. And then V sub 8 is 8 I sub 4 is equal to 0. Of course, we now consider this as the third equation. After writing your voltage law to this three loop 1, loop 2, and then loop 3, you will notice that we only have 3 independent equations. Take note that you can write more equations using the voltage law. As you can see it in the figure, look at your figure. You can write another equation for voltage law using the path A, B, C, F, E, and then A. Likewise, you have a closed path of C, F, E, and then D. As well as, shall we say, A, B, C, D, F, E, and then back to A. I mean the circuit diagram. What I mean to say is, going back to the circuit diagram, after writing your voltage law to this path, or loop 1, loop 2, and then loop 3, you will notice that you were able to formulate the first, the second, and then the third equations. You need 3 more equations. But look at this one. This is one closed loop, isn't it? All of this, A, B, C, F, E, and then A, is one loop. So you can produce another equation for that. Likewise, this is another closed loop. E, D, C, F, and then back to E. This is another equation, isn't it? Of course, you can trace the voltage using A, B, C, D, up to A. That is another equation. Meaning to say, you can produce many more equations considering closed path. And in fact, you already have 6 equations. But you will notice that if you solve these 6 equations using only the voltage law, later on, some equations will be reduced into the same equation. Meaning 2 or more equations maybe after solving the equation simultaneously, you will notice that the resulting equations are the same, so that as a result, there will be you will notice that you will have a total of available equations less than the remaining unknowns of your equations. So meaning to say, you cannot proceed further. The reason is because to solve the required current, you need to apply both the voltage law and then the current law. That's why my suggestion is, my advice is, you always write the voltage law using only the the loop of your circuit. This is one loop, this is second loop, this is another loop. After which, produce the remaining required equations using the current law. The current law now, let us apply the current law. Let us say apply the current law to node, let us say node, say C. Node C. At node C, you will notice that I sub 1 is entering node C, while I sub 2 and I sub 3 are both leaving node C. Current law simply states that the algebraic sum of all the current about a point or node or junction is equal to 0. So in other words, all you have to do is to equate those entering current with those leaving current. I sub 1 is entering I sub C, I sub 2 and I sub 3 are leaving node C. And therefore, the current equation there must be I sub 1 is equal to I sub 2 plus I sub 3. You now have the fourth equation. Apply the current law to node, let us say node D. Node D. The current equation at node D is equal to I sub 4 is equal to I sub 2 plus I sub 5. You now have the fifth equation. Of course, applying the current law at node F, let us say apply current law to node F. The current equation is equal to, as you can see it, I sub 3 is equal to I sub 5 plus I sub 6. You now have the sixth equation. You have 6 equations, 6 unknowns. Of course, all you have to do is to solve these equations simultaneously. The method of solving this, of course, rely on your skills of solving linear equations in 2 or more unknowns. There are methods, of course, in algebra. There are methods. You can make use of determinant, and so on and so forth. But in my case, I am more of using elimination by substitution, because you can apply the method, what is this, to any number of unknowns. Of course, when there are when you have a very complex circuit and there are so many unknown currents, it will be more difficult to determine or obtain the values, because you will need what is this method, of course, using advanced algebra, probably by matrix. Of course, it is more difficult. Now, in this case, take note, you now have equation 1, 2, 6, and you have to determine the values simultaneously. When you use the elimination by substitution, you must have some, what is this, systematic steps in the elimination process, because if you do not have a systematic way of eliminating the unknowns, what result is that you go back to some quantities or unknowns which you have already eliminated, and then suddenly the same unknown reappears in the equations that you are working on, meaning we got lost along the process. Okay, let us proceed with elimination. Although this is actually algebra, but I would like to show to you how to proceed solving these 6 independent equations, 6 unknowns, so that you will also have some ideas of how to systematically solve the equations to arrive at an answer. First, we have to decide where to begin with the elimination process. Take note, the currents has subscripts of 1, 2, 3, and so on. So you can decide to eliminate 1 followed by, I sub 1 followed by I sub 2, and so on and so forth. Or you may choose to eliminate I sub 6 followed by I sub 5, and so on and so forth. Say for example, in this case, equation 1, equation number 4 is expressed in terms of I sub 1. So, let us say, I would like to start eliminating I sub 1. So what I am going to do is this one, like this. I would say, let us say solving the 6 equations simultaneously. My first step, of course, is I would say substitute equation number 4 to equation number what? Equation number 1. Why number 1? Of course, you begin substituting the value of I sub 1 to all equations containing I sub 1. And you will notice that equation number 1 has I sub 1 as an unknown. So we substitute the value of I sub 1 of equation 4 to equation 1. It must be 24 minus I sub 2 plus I sub 3 minus 2 I sub 2 minus 4 I sub 4 is equal to 0. And then simplify the equations or combine similar terms. It becomes 24 minus, this is negative 2, this is negative this is negative 1 I sub 2. Okay, I sub negative 2, negative I sub 3, negative 2 I sub 2, minus 4 I sub 4 is equal to 0. It becomes 24 minus, this is minus 3, I sub 2 minus I sub 3, and minus 4 I sub 4 is equal to 7. Of course, we now call this as equation number 7. You are through with equation number 1. So what you are going to do now is, you cross out equation number 1. Cross it out. Why do you have to cross out equation 1? The reason is, if you are not going to cross it out, later on you may have, you can go back to the same equation if you do not cross it out now. So my advice is, you cross it out so that you cannot go back to equation 1. Because if you go back to equation 1 later, that's the time that some of the unknowns that you have already eliminated reappears in the process. The next one now is, you substitute again the value of I sub 1 of equation 4 to the next equation containing I sub 1. If you look at equation 2, there is no I sub 1. So skip. You proceed to the third equation. The third equation, as you can see, it has no I sub 1. Then move to the next one. Of course, you cannot substitute I sub 1 of equation number 4 to equation number 4. Of course, the next therefore is to look at equation number 6. And equation number 6 has no I sub 1. So meaning, finally, you are through eliminating I sub 1. What you are going to do next is, you cross out also equation number 4. You will notice now, if you look at the remaining equations, you only have equation 2, 3, 5, 6, and then 7. And you also have 5 unknowns. The next one is, because we started eliminating I sub 1, ang sunod, the next one that we are going to eliminate, of course, is I sub 2. So we choose which equation is to be used in eliminating I sub 2. Of course, we choose an equation which is easy to substitute the values. We cannot choose equation number 2, because in equation number 2 there are 1, 2, 3, 4 terms. Of course, the best equation to use is equation number 5, because in equation number 5, your I sub 2 is equal to I sub 4 minus I sub 5. Isn't it? Your equation 5 is I sub 2 is equal to I sub 4 minus I sub 5. So we can start eliminating I sub 2 by using equation number 5. What you are going to do now is, you substitute equation 5, meaning I sub 2 of equation 5 to equation, which equation? Of course, the first one is equation number 2, because equation number 2 has I sub 2. It should be equation number 2. We rewrite equation number 2. We say 4 times I sub 2 is equal to I sub 4 minus I sub 5. And then minus 10 I sub 3 plus 8 minus isob 5 is equal to 0. And then, the next one is, we simplify these equations. We continue, we have 4 isob 4 minus 4 isob 5 minus 10 isob 3 plus 8 minus isob 5 is equal to 0. And then let us combine similar terms. Our equation becomes 4 isob 4 minus 5 isob 5 minus 10 isob 3 plus 8 is equal to 0. We may call this as equation number 8. You are through with equation number 2. Let us cross it out also. Cross out equation number 2. Next is, we substitute the value of equation number 5 to the next equation containing isob 2. Equation number 3 has no isob 2. So we proceed to the next one. The next equation, of course, is isob 6. Equation 6 has no isob 2. Okay, we proceed to the next one. And then equation 7. So we say, let us substitute equation 5 to equation number 7. Okay, 7. Equation number 7. And equation number 7 is 24 minus 3 times isob 2. Isob 2 is isob 4 minus isob 5. And then minus isob 3. Isob 3 minus 4 isob 4 is equal to 0. And then let us simplify the values. It becomes 24 minus 3 isob 4 positive 3 isob 5 minus isob 3 4 minus 4 isob 4 is equal to 0. And in combining similar terms, it becomes 24 minus 7 isob 4 plus 3 isob 5 minus isob 3 is equal to 0. We can say now that isob 3 is equal to 24 minus 7 isob 4 plus 3 isob 5. Let us call this as equation number 9. Equation number 9. Again, let us also cross out equation number 7. The next equation, no more equation. We do not have equation now that containing isob 2. So we are now through with isob 2. Likewise, we can cross out equation number 5. Cross out equation number 5. The remaining equations are equation number 3, equation number 6, equation number 6, equation number 8, and equation number 9 with 4 remaining unknowns. The next a known to be eliminated is I sub 3. Of course, we can make use of, we can equate equation number 9 and equation number 6. So we say equation number 6 is equal to equation number 9. The values therefore will be I sub 5 plus I sub 6 is equal to 24 minus 7 I sub 4 plus 3 I sub 5. And then let us combine similar terms. This one becomes 6 I sub 5, 6 I sub 5, and then plus I sub 6 plus 7 I sub 4 minus 24 is equal to 0. Correct? 5, this is I sub 5, I sub 5, 4 I sub 5 plus I sub 6 plus 7 I sub 4 minus 24 is equal to 0. Because this is equation number 10. Let us eliminate, ano ba? Substitute equation ano? It is not systematic to substitute equate equation 6 and 9. In that case, we have skip equation number 8. Never mind. Let's proceed with that. Let us make use of equation 6 in eliminating equation I sub 3. It must be equation 6. Let us substitute equation 6 to equation 8. And the equation will be 4 I sub 4 minus 5 I sub 5 minus 10 times quantity I sub 5 plus I sub 6. And then plus 8 is equal to 7. And then we simplify this equation. It becomes 4 I sub 4 minus 5 I sub 5 minus 10 I sub 5 minus 10 I sub 6 plus 8 is equal to 0. And then combining similar terms, we will have 4 I sub 4 minus 15 I sub 5 minus 10 I sub 6 plus 8 is equal to 0. We now have equation number 10. We eliminate equation number 8. And then we equate now. We substitute rather. Let us substitute equation 6 to equation 9. So it will be I sub 5 plus I sub 6 is equal to 24 minus 7 I sub 4 plus 3 I sub 5. 24 minus 7 I sub 4 plus 3 I sub 5. Okay. And then is equal. And then we combine similar terms. Ano to? Magiging 7 isob 4 minus 2 isob 5 plus isob 6 minus 24 is equal to 0. Equation number 11. 1, 2, 3. 1, 2, 3. Okay. Let us say I sub 4 is equal to 24 plus I sub 6 24 minus I sub 6 plus 24 plus 2 I sub 5 minus I sub 6 all over 7 is equation 11. We are now through eliminating I sub 3. So let us also eliminate here. From here, we eliminate equation number 9. And finally, we eliminate likewise equation number 6. You will notice that the remaining equations are 11, 10, and 11, 10, and 11, equation 3, equation 10, and then equation 11 with the remaining unknowns I sub 4, I sub 5, and I sub 6. Okay. Which equation? In equation number 3, I think we can make use of, let us consider this as equation 11. And then let us use equation number 3 to eliminate I sub 4. Our equation number 3 is equation number 3, let us rewrite equation number 3 in terms of I sub for I sub 4. I sub 4 in equation number 3 is equal to 8 plus 5 I sub 6 minus I sub 5 all over 8. This is our equation number 3. Take note, the remaining equations are equation 3, equation 11, and then equation number 10. These 3 equations. And we are going to make use of equation number 3 to eliminate I sub 4. What we are going to do now is, we substitute 3 to equation equation number 10. 3 to equation number 10. And the value is 4 times quantity. I sub 4 is 8 plus 5 I sub 6 minus I sub 5 over 8. Equation number 14. Tapos minus 15 I sub 5. 15 I sub 5 minus 10 I sub 6 plus 8 is equal to 0. So we multiply both sides by, of course, this one is 4 and 8. So that becomes multiplying both sides by 2. Multiplying both sides by 2. Multiply both sides by 2. The result is 8 plus 5 I sub 6 minus I sub 5 minus 2 times 15 I sub 5 minus 2 times 10 I sub 6 plus 2 times 8 is equal to 7. So it becomes 8 plus 5 I sub 6. Let us combine similar terms now. Let us combine similar terms. This is 30 I sub 5 plus minus 1. So 30, 31. Negative 31 I sub 5. And then this one is 2 times 10, 20. Negative 20 I sub 6. Negative 20. Positive 5 I sub 6. So that becomes negative 20 minus 5. So it becomes negative 15 I sub 6. And this is 16 plus 8 plus 24 is equal to 0. Okay, this is 30, negative 30, negative 1, so this is negative 31. This is negative 20, minus 5, minus 15, I sub 6, and then plus 24 is equal to 0. Okay, so it must be I sub 5 is equal to 24 minus 15 I sub 6 over 31. This is equation number 12. Equation number 10 is now out. We cross out equation number 10. We substitute now equation number 3 to equation number 11. Now, when I say substitute equation number 3 to equation 11. Equation 11 is 7 times quantity. 8 plus 5 I sub 6 minus I sub 5 all over 8. Minus 2 I sub 5 plus I sub 6 minus 24 is equal to 0. If we multiply both sides by 8, the result is 7 times 8 plus 7 times 5 I sub 6 minus 7 times I sub 5 minus 8 times 2 I sub 5 plus 8 times 8 I sub 6 minus 8 times 24. This is equal to 0. And then, ayan, magiging, this is 56, this is 35 I sub 6, this is 7 I sub 5, this is 16 I sub 5, plus 8 I sub 6, minus 160, 24, 184. No. Ayan. 32, 3, 16, 192 is equal to 0. And then combining similar terms, we have 35 minus 16. Ayan. 35 minus 15, 20, 19. So this is, I don't know, minus 7, minus 16, this is negative 23. Negative 23 I sub 5, and then positive 35 plus 8, 43. 43 I sub 6, minus 192 minus 56. This is 192 minus 56. 12, 6. This is 8, 3, 136 is equal to 0. So that this is now equation number 13. Okay. Equation 13. Finally, we cross out equation 11. We are through eliminating I sub 4, so we cross out likewise equation number 3. And then, you now have only equation 12 and 13. This time, you only have, you substitute equation 12 to equation 13. And it becomes minus 23 times quantity. I sub 5 is 24 minus 15. I sub 6 over 31. I sub 5 plus 43 I sub 6 minus 136 is equal to 0. We multiply both sides by 31. Multiplying both sides by 31, we will have minus 23 times 24, positive 23 times 15, I sub 6 plus 31 times 43 I sub. Okay, to continue. Of course, this is from the previous recording regarding the application of a voltage law and then the current law to a given direct current circuit. Of course, from here, I sub 6 is found to be 2.841478 amperes. The positive sign of this current simply indicates that you have or we have correctly choose the direction for current I sub 6. Otherwise, the negative value of which will indicate that we have chosen a wrong direction. Now, of course, from equation number 12, look at your equation number 12. From equation number 12, your I sub 5 will be negative 0.600715, or this is 0.600715 ampere. The negative sign, of course, indicates that we have chosen a wrong direction, meaning the actual direction of I sub 5 should be going to the right instead of going to the left. Similarly, your I sub 4 may be solved from equation number 3. If you look at your equation number 3, this is for I sub 4. Your I sub 4 is 2.70834 amperes. Of course, the direction of which is downward. From equation number 6, our I sub 3 is 2.24 amperes. The direction of which is, of course, going to the right. From equation number 5, your I sub 2 is 3.301549 amperes. Again, this is positive, meaning to say we have chosen a correct direction. It should be downward. And from I sub 4, finally, we have I sub 1 is equal to 5.5312 amperes upward. Now, with these branch currents known to us by this time, of course, it is easy to determine the voltages across the resistors. Say for example, across the 2 ohm resistors, 2 ohm resistor, your V sub 2 is given by 2 I sub 1, and this is equal to 11.08 volt. Our V sub 10, the voltage across the 10 ohm resistor is 10 I sub 3, and the value is 22.41 volt. Also with V sub 5, across the 5 ohm resistor, this is 5 times I sub 6, and the value is 14.21 volts, and so on. Of course, you can just determine all the remaining voltages. I would like you to be aware of how to determine the voltage across any 2 nodes or junction of the circuit. By the way, before we go on with that, of course, we may choose to check whether the values of our currents are correct, because it is possible that along the way we committed a mistake or an error in the solution, and probably the values here are not correct. So one way of checking this, the values, is to apply the voltage law or the current law to other, the voltage law. You can apply the voltage law to other paths other than those that we have already considered. Say for example, if we would like to apply, we may apply, say for example, we would like to check whether the values. Of course, one way, say for example, let us apply the voltage law to path. Say for example, I would like to apply the voltage law along the path A, B, C, down to F, to E, and then back to A. Of course, the voltage law as applied to this closed path should be 0, isn't it? Then we begin by starting from A down to B. This is positive 48 for the voltage source. From B down to C, this is minus B sub 2. And from C down to F, minus B sub 10. and then from F down to E minus V sub 5. From E down to A or back to A, no resistor or there is no circuit element, so we now proceed to equating this to 0. And let us see whether the voltage along the algebraic sum of the voltages along this closed path of the circuit is also equal to 0. So we check this one. For the meantime, let us put a question mark whether this one is equal to 0. So we check positive 48, V sub 2, we have already computed V sub 2, 11.08, V sub 10 is found to be 22.41, and then V sub 5, V sub 5 is 14.21. So this is 15, 11 plus 22 plus 14, this is 39, 40, 47, 11, 33, 47, 0.21, 0.41, and 0.08 is 1. So this is equal to 0 is equal to 0. That confirms that the values that we have obtained for the branch currents are all correct. Similarly, you can apply the current law to other nodes which we have not considered in the solution. And of course, the current law should confirm also that the values are correct. Now, how do we determine the voltage across two nodes? Because the voltages that we have considered here so far are only referring to the voltages across the resistor. Now, suppose we would like to determine the voltage from C to E. Suppose for our required C, we would like to determine the voltage from C say for example, we would like to determine the voltages V sub EC and V sub, shall we say, DF. To determine these voltages or the voltage across two nodes, all you have to do is to trace the voltage from one node to the other node. Say for example, for V sub EC, all you have to do is to trace the voltage from E down to C using any path of the circuit. Say for example, in this particular circuit, I may choose to trace the voltage from E down to C using the 48 volt source and then the 2 ohm resistor. All I have to do is you write the voltage from E to C. So you start from E down to B. From E down to B, you have positive 48 volts. Meaning to say, the voltage that you will encounter from E down to B is the 48 volt source. So you say and you are tracing the voltage from from A down to B, and it is from negative to positive. That is why it is positive 48. To proceed further from B down to C, this is negative V sub 2. Why negative V sub 2? Because you are tracing, or shall we say, I am tracing the voltage from positive terminal to negative terminal. And the value is now 48 minus V sub 2. V sub 2 is 11.08 volts. Therefore, V sub EC is equal to 48 minus, so 48 minus 11 is 37. So this is 36.92. Is that correct? 11, 47, 92, okay. Volt. This is 36.92 volts. And all you have to do is to interpret the positive sign. Take note that you are tracing the voltages from, you are tracing the voltages in that you are assigning positive values for those that are traced from negative to positive, and positive sign for those that are traced from positive to negative. Now, in tracing the voltage from E down to C, you have a positive sign of 36.92. It means to say that your C is positive with respect to E, which is true because in going from A down to B, you have positive 48 volts, and then minus the 11.08, so you still have a positive value of 36.92 volts. It means to say that C is positive with respect to E. Of course, you can trace the voltage from E down to C using other path. If you choose other path, you will have to do it in the same way, and you will notice that you will have the same value. Say for example, or you may choose to determine the voltage from E down to C using the path E down to D, and then from D down to C. The voltages will be positive V sub 8 and positive V sub 4. Of course, the value should be 36.92 volts also. C is positive with respect to E. Okay, I hope this is clear insofar as application of the voltage and the current law to a circuit. Of course, there are other methods that we can, there are other methods that can be applied. And these two methods are modification of the application of the voltage and then the current law. The two methods are either nodal or using the Maxwell-Misch equation. We will have that by next time.